Welcome back to The Explainer. Look, if you're a focused learner gearing up for a major chemistry exam, you are in exactly the right place. Today, we're running through the ultimate chemistry exam prep boot camp. We're going to take a journey from the macro, the stuff we can actually see and touch, all the way down to the micro, those invisible atoms that make up our entire universe. I promise you some seriously high-yield study strategies to get you exam ready, so go ahead and grab your notebooks.
Okay, let's dive into this. We've got a structured roadmap today, designed specifically to help crush that exam anxiety. We're covering 6 key areas: matters, states, and classifications, measurement and notation, laws and atomic theory, the magic of the mole, stoichiometry practice, and finally, solutions and molarity. Basically, we'll start with the visible world and zoom all the way down to your essential laboratory calculations.
All right, Section 1, Matter, States, and Classifications. Let's look at the physical world.
To quickly memorize particle behavior for the test, try visualizing matter in its 3 physical states like this. Think of solids as a tightly packed, totally orderly stadium crowd. The particles are held very close together, super organized, with almost zero freedom to move. Now liquids, they're more like a mingling party. The particles are still close to each other, but they can move around freely, which is exactly why liquids take the shape of whatever container you pour them into. And finally, gases. Gases are your chaotic bumper car arena. The particles are moving fast, they're far apart, and they will completely occupy whatever space they're given.
Now, beyond physical states, we have to classify matter at the bulk level by looking at mixtures. A homogeneous mixture is one where the components completely mix with each other, meaning the composition is totally uniform throughout. Think of the air you breathe, or a perfectly clear dissolved sugar solution. On the flip side of that, we have heterogeneous mixtures. Here, the composition is definitely not uniform, and you can usually see the different components, like if you were mixing salt and sugar together in a bowl or dirt and pebbles.
But what if it's not a mixture at all? Well, that brings us to pure substances. A pure substance is matter with a fixed composition, where all the constituent particles are the exact same in their chemical nature. These can be elements, like pure copper, which is just one type of atom, or compounds, like water, where different atoms combine in a very fixed ratio. Now here's your key exam takeaway. You can separate mixtures using simple physical methods, like filtration, but you absolutely cannot separate pure substances that way.
Moving right along to Section 2, Measurement and Scientific Notation. Think of this as your scientific toolkit.
Now, what's really interesting about this slide is that these 7 SI base units literally form the foundation for all derived scientific measurements globally. Since 1960, the scientific community has relied on this exact international system of units. So whether you're measuring length in meters, mass in kilograms, or temperature in kelvins, every single other unit you'll encounter on your exam, stuff like density or volume, it's just a mathematical combination of these base 7.
Of course, as chemists, we deal with astronomically huge numbers of atoms and impossibly tiny masses. So how do we write those down without breaking our pencils? Scientific notation. Here are your quick exam hacks to nail this every time. Step 1. Move your decimal point to create a number between 1.000 and 9.999. Step 2. Just count how many places that decimal jumped. That is your exponent. Step 3. If you move the decimal to the left, your exponent is positive. If you moved it right, it's negative. Practice this because I promise you'll use it constantly.
Oh, and while we're talking about numbers, here's a rapid-fire tip on significant figures. Significant figures represent the actual certainty of your lab measurements. Just remember these golden rules. Non-zeros always count, zeros trapped right between digits count, but those tricky trailing zeros at the very end of a number, they only count if there is a decimal point somewhere in that number. This is exactly how we honestly report the uncertainty in our laboratory math.
All right, Section 3, Laws and Atomic Theory, the Rules of Combination.
I absolutely love this timeline. It shows this rapid, brilliant burst of discovery. We start in 1789 with Lavoisier's conservation of mass, proving matter is neither created nor destroyed. Then Proust gives us definite proportions in 1799, showing compounds always have a fixed weight ratio. By 1803, Dalton drops multiple proportions on us. And quickly after that, we get Gay-Lussac's gaseous volumes and Avogadro's law. These foundational laws, which all came from those exact measurements we just talked about, were the ultimate proof that invisible atoms actually dictate chemical combinations.
And all those laws totally culminated in John Dalton's atomic theory in 1808. He essentially proposed that matter consists of indivisible atoms, that all atoms of a given element have identical properties, and that compounds form when different atoms combine in fixed ratios. Chemical reactions? They're really just a reorganization of these atoms. Now, obviously, science evolves, and we later learn that atoms can actually be divided into subatomic particles, but Dalton's framework completely revolutionized chemistry forever.
Let's move to Section 4 and see how this builds. This is the magic of the mole, bridging the gap between the micro and macro worlds.
So, the crucial point here is understanding what a mole actually is. I know it sounds intimidating, but it is literally just a counting unit. Think of the word dozen. It always means 12 items, right? Well, a mole always means exactly 6.02214076 times 10 to the 23rd elementary entities. It's just a dozen scaled way, way up to handle the unbelievably tiny size of atoms.
Seriously, just look at this number written out without scientific notation. 602 sectillion, 213 quintillion, 670 quadrillion. That is massive. This awe-inspiring magnitude is exactly why we spent time mastering scientific notation earlier. You absolutely do not want to be writing all those zeros on your exam paper.
And this brilliantly illustrates the real magic of the mole. It's what makes physical lab work possible. See, atomic mass is the mass of a single tiny atom measured in unified mass units, or U. But molar mass is the mass of one full mole of those atoms measured in grams. The absolute magic here is that the numerical value is exactly the same. You literally just swap the U from the periodic table with grams, and suddenly you can weigh out exact numbers of atoms using a standard macro-scale lab balance.
On to Section 5, Formulas and Stoichiometry Practice. Time for the chemical recipes.
So the crucial point on this slide is distinguishing between the two types of chemical formulas you're going to be tested on. An empirical formula is the simplest, most reduced whole number ratio of atoms in a compound. But the molecular formula, that tells you the exact number of atoms actually present in a single molecule. A really common exam setup is giving you percentage composition data. You'll calculate the empirical formula first from that percentage, and then use the molar mass to find the true molecular formula.
Let's intentionally slow down for a second. We're going to walk methodically through a classic exam stoichiometry problem, finding the limiting reagent. Imagine you're given 50 kilograms of nitrogen gas and 10 kilograms of hydrogen gas to make ammonia. Step 1. You must convert those given masses into moles. Always go to moles first. Step 2. Look at your balanced equation to find the required mole ratios. Here, 1 mole of nitrogen needs 3 moles of hydrogen. Step 3. Compare what you actually have to what you need. In this specific case, if you run the numbers, you will run out of hydrogen first. That makes hydrogen your limiting reagent, which completely dictates the maximum amount of ammonia you can possibly form.
Finally, Section 6, Solutions and Molarity Calculations. The liquid mixes.
Okay, pay very close attention to this critical exam distinction between molarity and molality. They sound similar, but they are traps. Molarity, with a capital M, is the moles of solute divided by the liters of solution. Because it's based on volume, molarity actually changes slightly with temperature due to liquid expanding or contracting. But molality, with a lowercase m, is moles divided by kilograms of solvent. Because mass doesn't change with temperature, molality is totally unaffected by heat. That is a guaranteed trick question on your exam.
And this brilliantly illustrates how straightforward these calculations can be if you just stay organized. Let's find the molarity of 4 grams of sodium hydroxide dissolved in 250 milliliters of water. Step 1, identify your data. Step 2, find the molar mass of sodium hydroxide, which is 40 grams per mole. Step 3, convert that 4 grams to moles, giving you 0.1 moles. Step 4, convert your 250 milliliters of water to liters, giving you 0.25 liters. Step 5, the final piece of the puzzle, divide your moles by your volume. 0.1 divided by 0.25 gives you a 0.4 molarity solution. Boom! Easy, structured, and 100% correct.
We have covered some incredible ground today in this explainer, from the macro states of matter all the way down to the micromath of molarity. As we continue to master the invisible rules of atoms and molecules, what infinite, life-saving chemical combinations will your generation synthesize next? Keep that in the back of your mind as you prep for your exams. You aren't just memorizing numbers and formulas. You're learning to manipulate the literal building blocks of the future. Thanks for joining me on this deep dive, and hey, happy studying!